This is lecture number 3 in chapter 1, or the first lecture of chapter 1. And here we're looking at the pyramid of Kukulkan in Chichen Itza on the Yucatan Peninsula, constructed by the Mayan culture. And where we find these kinds of pyramids all around the world. The pyramid was a favorite ancient structure, and they have survived many hundreds of years, amazingly. That most of these structures, if not all, have astronomical significance. This particular one was aligned to the equinoxes, and it had 365 steps, 91 steps on each side, and then one final step to the top. And this particular one had a serpent's head at the bottom here, if we can see at the bottom of the staircase. And on the equinox, the sun would hit just perfectly along these corners to create a serpent-like image all the way down this line, and that would only happen perfectly on the equinox, and hence that would designate that date, which had a special significance to the culture. But the point being right here is that the 365 steps shows that the Mayans were very well aware of the length of the year and other astronomical significances. Here's a pyramid of the niches, also in Mexico. 365 niches. I guess each niche is these holes, and again showing a particular awareness of astronomy. Here's the Very Large Array in New Mexico, a current setup as we study radio astronomy. The reason why we study radio astronomy is there is a hole in our atmosphere that basically allows radio waves to come through very much less attenuated than other frequencies of the electromagnetic spectrum. And you can see that there are 365 antennas for this very large array. No, I'm just kidding. No, not 365 antennas, but it does show a modern observance of astronomy and an attempt to collect that data. Here are telescopes on Mauna Kea in Hawaii, used strictly for visible astronomy. Again, looking through the atmosphere, our atmosphere, trying to pick up what it can of the sky, and we can see that throughout history, humankind has been interested in the sky. Here's the Hubble telescope. Works for all astronomy since it's outside of our atmosphere. You can see all the wavelengths and all the frequencies of the electromagnetic spectrum, and hence it can gather all sorts of data on the universe. An excellent instrument for studying the universe. And what do you see? Well, if you look at the visible spectrum, you might see something like this, as we mentioned in the last chapter. This is the constellation of Orion. It's very interesting in the fact that you can associate figures with it and some kind of pattern that helps determine the time of year. But if you were an ancient astronaut, an ancient astronomer, you would be looking up into the skies every night, and pretty much a lot of your time would be spent thinking about what's going on up there and why we see what we see. And one of the more important and prominent features in the sky would be indeed the moon. The phases of the moon, since the moon changes its look every day, you would see the moon go through its phases, and this would be of ultimate interest to an ancient astronomer. Here we're looking at a diagram of the Earth-Moon system, looking down from the North Pole on the top of the Earth here, with the Moon heading eastward around, or counterclockwise around in this direction. The Sun's light coming from the right. So we can see at various times, depending on the Moon's position with respect to the Earth and the Sun, we would see different phases of the Moon. As the Moon is illuminated, basically always half illuminated from the Sun, but as we see it, it goes through the phases. And at the new Moon here, the Moon is in line with the Sun and the Earth, and hence we would generally not see any of the surface of the Moon, because we'd be looking at the back side, and also this would occur during the daytime where the Sun's light is scattered in a diffuse way throughout the sky, so the Moon and the stars cannot really be seen in the daytime. As the Moon travels eastward around the Earth, we see different parts of illumination of the Moon going through a crescent stage to the first quarter, following to a full moon, through a gibbous phase, back through a crescent phase, back to the new moon. For the new moon to the first quarter phase is approximately 1 week, and maybe that had a significance or a bearing on the determination of the length of the week. Here's another look at the same diagram, probably a little bit clearer. As we have sunlight coming from the right, North Pole, we're looking down on the North Pole of the Earth, and the Earth is turning eastward on its axis. And we would see the Moon at these different phases in this position with respect to the Earth and the Sun. And we can see that the new Moon would occur at noon in the day of the Earth, if we're in that position, because that's when we would be facing that position. We would recognize the crescent moon on our overhead meridian at 3 p.m., the first quarter moon at 6 p.m. So if you're looking south over your overhead meridian, which is passing from north to south over your head, as you're facing south, if the moon were to cross that overhead meridian at 6 p.m., then it must be a first quarter moon. If it crosses your meridian at 9 p.m., waxing gibbous. At midnight, a full moon. Between midnight and 6 a.m. would be a waning gibbous, and a last quarter moon at 6 a.m. and a waning crescent from 6 a.m. to 12 noon. So in essence, when the moon crosses your overhead meridian, is a sense of time and a sense of the clock in the day. If we look to the right here, where the moon is less than half illuminated as seen from the Earth, we call that a crescent phase. And when the moon is more than half illuminated as we see it from the Earth, that is a gibbous phase. As the moon increases in illumination from day to day, we have a waxing moon. And as it decreases in illumination, say from the full moon to the new moon, we have a waning moon. Combining these terms, we would see that in this first quadrant, as the moon goes from a new moon to a first quarter moon, we have a waxing crescent, waxing meaning gaining in illumination, and crescent meaning less than half illuminated. First quarter moon would be half illuminated as we see it, and from that point on it would go through a waxing gibbous stage, where it's increasing in illumination from day to day. Gibbous meaning more than half illuminated as we see it, so for about a week it goes through that stage, finally culminating in a full moon, which is fully illuminated as we see it from our perspective. Then it goes through a decreasing illumination in successive nights, so it would be a waning gibbous, even though it's still more than half illuminated. So hence it's a gibbous moon. And then we have a last quarter moon where it's half illuminated on our overhead meridian at 6 a.m. And then for the next week or so, it goes through a waning crescent phase where it's still decreasing in illumination from day to day, but the moon itself is less than half illuminated for the whole stage. Here's a look looking down at the Sun, Earth, Moon system, and with this we're going to define the terms for the month. Now we can say that if the moon were to go around the Earth strictly 360 degrees, so purely strict 360 degrees with respect to the distant stars, we call that a sidereal month. So that's a pure one revolution around the Earth with respect to a very, very distant point, a distant star. But if the moon went one revolution around the Earth with respect to the sun, it would have to travel an approximately extra 30 degrees or so, because in the course of that 1 month, the Earth has revolved around the sun approximately 30 degrees, or 360 degrees divided by 12 months, so about 30 degrees. And hence, the moon would have to travel at an extra 30 degrees in order to line up with the Earth and the Sun again, in order to be synchronous with that. So that extra 30 degrees of the sidereal month would give us the synodic month, the month in which the moon is in sync with the Sun. The synodic month is 29.5 days. The sidereal month is 27.3 days. The reason for the extra 2.2 days is that extra 30-degree path that the moon must travel in order to be a synodic moon. If we were to observe the moon, that's what we see, the synodic month, 29.5 days. We will recognize that the moon is changing position then in that 29.5 days. So over the course of each day, the moon is going to move 129.5 of its revolution around the Earth. So that means the next day the moon will be in a different part of the sky, and if we relate one rotation of the Earth as 24 hours, then the moon would have moved 129.5 of a day, which would be, in terms of hours, 24 hours divided by 29.5, which is 50 minutes. So the moon basically will rise 50 minutes later each day because its position is changing by 50 minutes in the sky each day. Now, as we said before, an angular distance of your hand at full extension, the expanse of your hand is 15 degrees. So 50 minutes would be about from your thumb to your ring finger, and hence in the sky the moon will move that much angle in the sky every day. Here's the conditions for a total solar eclipse. Every once in a while the moon is perfectly between the sun and the Earth, and hence it's possible that the moon's shadow might make its way onto the Earth, and at that point, within that shadow, you would not see the sun. We call that the moon's umbra. So the moon's main shadow is the moon's umbra, and if you're within that, you would see a total solar eclipse. There's a way, or there's possibility that only part of the sun is being blocked by the moon, and hence you would see part of the sun's light, and in that partial shadow you would see a partial solar eclipse. That is called a penumbra. Here's a look at a solar eclipse impacting onto the surface of the Earth. So people who are within this shadow right here would see the total solar eclipse. In order to have a total solar eclipse, you need a new moon. In other words, the moon has to be between the sun and the earth. The moon must be close enough for its shadow to make it to the earth. So it must be near perigee, which would be its closest approach to the earth. The moon is traveling in an elliptical orbit around the earth. So every once in a while it's at its furthest distance from the earth, its apogee, and every once in a while it's at its closest distance, its perigee. The moon's shadow would not make it to the earth if it were at the apogee. So for the shadow to make it to the earth, the moon must be close to its closest approach, perigee. The moon must also be at a node on the ecliptic. The moon's angular expanse is 1/2 degree. However, as we'll note real soon, that the orbit of the moon is not perfectly in the plane with the sun and the earth, and it's inclined to the ecliptic plane by 5.2 degrees. Hence, even though you might have a new moon, the moon might not be blocking the sun. So here's what we mean by nodes. If we look at this angular path of the moon's orbit at 5.2 degrees with the plane of the Earth's orbit, a node would be where that orbit intersected with that plane at points A and B on this path. We would need the moon to be at A or B between the Earth and the sun for a solar eclipse to occur. These would be called nodes. So since the moon's angular size is only 1/2 degree, it's possible it could be off the plane of the Earth's sun by more than 1/2 degree, and hence the moon's shadow would never touch the Earth. It would go beyond the Earth like this. Hence, you'd have a new moon, but no eclipse. So most of the time, this is what occurs, because 5 degrees is much bigger than 1/2 degree. So most of the time, the moon would not block the sun. But these nodes are moving as a course of time, and the total orbit of the moon is precessing, just like we talked before about the Earth precessing, the moon's orbit precesses as well. So this angle of the moon's orbit is always moving around and completes one precession in 18.6 years. So even though at some point you might find some regularity for solar eclipses, that's going to be offset by the fact that this precession is taking place. So the nodes are changing, and so sometimes you might have more solar eclipses in some length of years, and then it might be rare for a few years after that. Certainly, though, one of the more astronomical, beautiful astronomical phenomena is a solar eclipse, and it must have been very beautiful and frightening at the same time to ancient peoples who did not understand what was going on. But as the moon passes in front of the sun and blocks it out, then all of a sudden you can see features of the sun that you couldn't see before, namely the solar corona and possibly some stars in the sky. Here's a solar eclipse, but we have a little bit of the sun's light coming through because on the edge of the moon's not perfectly round. It actually has craters, and so on this edge we just happen to have a large enough crater so that the sun's light is coming through, and hence the image looks like a wedding ring. Here's a bigger effect of that, so the crater over here must be larger. Evidently, this wedding ring, whoever has this wedding ring, has got more money. Here's some future solar eclipses passing around the Earth. We can see some distortion near the poles here because this is a Mercator projection of the Earth. Here's some of note. Actually, this one just passed July 22nd, 2009. Passed through China. The blue line indicates the totality section, and the green line would be a partial eclipse. So on July 11, 2010, we'll have another total solar eclipse here in the southern Pacific. Maybe if you travel to Chile or Argentina, then you know the very tip here, you'd be able to see that eclipse. May 2012, this is in red, so this must be an annular eclipse, which means that the moon's main umbra is not making it to the Earth, hence you don't have a total eclipse. The moon is going to be blocking the sun, but there will be some light of the sun all the way around the moon. November 13th, 2012, if you go to part of Australia, you'll be able to see that solar eclipse. May 10th, 2013, another part of Australia. Of course, this one's an annular eclipse as well, so it won't be as spectacular. November 3rd, 2013, go through Africa, like the Congo, you'd be able to see this total solar eclipse. It's only lasting 1 minute 40 seconds. October 23rd, 2014, partial eclipse in the North America. March 9th, 2016, go through Indonesia. Bingo. August 21st, 2017, a total solar eclipse through the center of the United States. If you don't like to travel, this one's coming right to you. Through the center of the United States, August 21st, 2017. Let's meet and take a van with all the class and go see this eclipse. If we start looking closer, we see that this eclipse is going to pass through Missouri, Kentucky, Tennessee, a little bit of Georgia and South Carolina, not too far from northern Alabama here. Let's keep on blowing this up here. In fact, the totality of this eclipse will go through Nashville, Franklin, Tennessee up here, and just north of Chattanooga. So you might want to make your reservations, your hotel reservations in Nashville now. They might be filling out 2017. In 2024, there'll be another total solar eclipse passing through the United States. Great, only 7 years later. This one passes through, if you're in Dallas, you'll see it. Little Rock, Arkansas, Cincinnati, Ohio, near there, and still, again, not too far from northern Alabama. So you just have to travel just beyond Memphis, and you find yourself in the totality region of this eclipse. If you missed that one, the next one through the United States would be August 12th, 2045. So 21 years later, we'll get another one. But I'm looking forward to seeing those earlier ones, 2017 and 2024. I hope to see this one too, but it's not guaranteed. This one's traveling south of North Alabama, so we'll go through Alabama. In fact, Montgomery would be a good place to see this one. And Little Rock, Arkansas, it gets hit again. So if you lived in Little Rock, you're going to see two of those eclipses that actually pass through the United States. There's Montgomery. So make your reservations now for hotels in Montgomery or Destin, Florida, maybe. August 12, 2045. We mentioned an annular solar eclipse. Here are the conditions for that. The moon still should be a new moon, and the moon should be at a node on the ecliptic, but the moon is now too far away from Earth for its umbra to reach the Earth, its main shadow to reach the Earth. So the moon must be near apogee, in other words, its furthest approach from the Earth. Here's a picture of an annular eclipse in Mexico in 2002. This was a total solar eclipse, but as the sun was setting, the distance of the light became further for this observer in Mexico, and hence it became an annular eclipse for that area. And you can see that the light of the sun creates a ring all the way around the moon. It could be beautiful in and of itself. So here's a summary of eclipses. A total eclipse, the moon totally blocks the main part of the sun. Annular eclipse, the moon's shadow does not reach the Earth, so a part of the sun is a ring all the way around the moon. And a partial eclipse, the moon is blocking partially the sun. You would still see a lot of brightness due to the rest of the sun, so you probably would want to use some kind of projection screen or lens to show this image of this partial eclipse, or use the special glasses. Here's an eclipse through binoculars. You never want to look directly at the sun, but you could look at the image created through these binoculars, and they're just kind of goofing around here to show the eyes. If you don't want to use lenses, you could use a pinhole effect. The pinhole uses the diffraction of light to focus light, and hence just a small opening creates that image, and hence this opening in this hand has created the image of the partial eclipse, and you can see it looks like the eye of this bird. This birch tree has a lot of small openings, all of them acting like pinhole cameras, and hence you can see all the partial eclipses from that image, and it looks pretty neat on the side of this barn. You could also have a lunar eclipse. A lunar eclipse occurs when the Earth blocks some or part of the sun's rays on the moon. Lunar eclipse will occur when the moon is at or near the full phase. In other words, the Earth has to be between the sun and the moon for this to occur. When the Earth lies between the sun and the moon in nearly a straight line, the Earth's shadow will conceal the face of the moon, and the Earth's shadow is much bigger than the moon's shadow. Hence, a total lunar eclipse can last for more than 1.5 hours, because the moon could reach that shadow in different parts, and the shadow is much bigger, so it would travel through that shadow, or the shadow would not move very much, and hence you'd have 1.5 hours, and partial eclipses can last for over 3 hours. In contrast, the solar eclipse, I think the maximum is about 7 minutes. Here's how it might look for a lunar eclipse. You have the moon, the Earth between the sun and the moon. The main umbra, the main shadow of the Earth, is encompassing the moon. If you're in the Earth's umbra, you see a total lunar eclipse. If the moon is in the Earth's penumbra, you see a partial lunar eclipse, at least from your perspective. For a total lunar eclipse, we must have a full moon on the ecliptic and it could be at apogee or perigee. It doesn't really matter because the Earth shadow will still reach it. So just a full moon on the ecliptic. Here's a look at a lunar eclipse taking place. Here's the moon. Here's the shadow beginning to impinge upon the moon. As we see over time, the Earth's shadow, some people have tried to measure the size of the Earth due to the curvature of the shadow. But the Earth's shadow is moving along the moon until it finally eclipses the whole moon. And actually at this time, you might actually see a reddish looking moon, which is kind of unusual. If you're thinking that the Earth is totally blocking the light from the sun, why would you see any color at all from the moon? Why wouldn't it just be black? And the reason is that that some of the light that goes through the Earth's atmosphere is being focused onto the moon, and that light, as you know from any sunset, is rather reddish. So there's kind of a sunset effect of this light being focused through the Earth's atmosphere onto the moon, making the moon appear reddish, sometimes called the harvest moon. If the Earth didn't have any atmosphere, then you would not see this effect. The moon would just be black. So since the moon doesn't have any atmosphere, we don't get this effect in the reverse situation. Here's a look at the moon going through a lunar eclipse, reaching this harvest or red moon effect, and then exiting from the lunar eclipse, finally with the moon going to full moon again. That concludes lecture number 3, the first part of chapter 1 on eclipses.